Hello everybody, it's Mr. H. Don't actually have the webcam hooked up right now, but I do have the mic going, and I am going to kind of walk through just with the screen share. I wanted to make a video that just kind of introduces everybody to quadratics. Of course, I looked all through YouTube and I just couldn't find one that I was satisfied with. There's lots of videos that give you information on how to do specific things, but as far as just a decent overview of kind of what we're doing, I didn't find. So I just want to take a moment to kind of go through some things. That way you have just a general idea of what we're doing, and then we can go from there. So I think the first thing to do is just to remind y'all that before we ever got to quadratics, we worked with straight lines, which specifically were linear equations, linear functions, and whenever we dealt with linear functions, there were different forms that could show up. There was standard form, which was technically ax plus by equals c, which we didn't really see a whole lot. What we saw most of the time was this slope-intercept form. And generally, if I ask in class what slope-intercept form is, people sometimes forget, but then whenever we start kind of writing it out, they remember oh yeah, it's just that y equals mx plus b. And if you remember, specifically m here is your slope, b is your y-intercept, and the x's and y's that you see here, the y and the x, represents different points that are going to be in that equation. So in other words, y equals mx plus b, whatever it may be, whatever these numbers are, they're going to define all of the possible points that can be on that line. So just to kind of clarify what I mean, say you had y equals 2x plus 5. So based off what we just did, you know the slope. 2 is the slope. And 5 is the y-intercept. And then your x and y that are here, what I mean when I say it sort of, this sort of identifies what can show up on that line. Since this is an equation, y has to be 2x plus 5. So specifically, y has to be 2 times x plus 5. So whenever you graph this, what you're actually doing is plotting all the possible points that describe this relationship. In other words, you have to think about this as a pair, which is why we talk about ordered pairs so much. You have to think about this as a pair of numbers. So remember, ordered pairs have an x part and a y part. And if you were to graph this, I'm just going to kind of sketch it here. It would be roughly something kind of like this. It would not actually be dotted. Okay, that's close enough. Okay, so you get the point. The line would look something like that, and basically every single point on this line would satisfy this. If you pick some point that's not on the line, over here, it's not going to satisfy this equation. It won't make sense. So for example, let's just say we pick the origin here, which is 0, 0. Try that. If you're trying to say that this is a point that is explained by this equation, you get 0 equals 2 times 0 plus 5, which gives you 0 equals 5, which is not true. So notice I picked a point, 0, 0. I picked an ordered pair. I put it in here, and because it wasn't on that line, it did make sense whenever I put it in there. And when I say put it in there, I substituted. I use that idea, that substitution property. So I wanted to show you that first, because when we start talking about quadratics, we kind of follow a similar vein of thought, which means there's going to be different forms that you have to know. There's certain things about these forms that help you. So with the straight lines, we had slope, we had the y-intercept, and the x and the y identified all of the points. Well, X and Y continues to identify all the points. It's just that whenever we start working with quadratics, there's just other information that we have to get out of it. And that's where we're going to kind of move on to now. So specifically here, we're going to look at quadratic equations. Now, I want to stress that you can technically come across other sort of phrases that mean different but similar things. And so in other words, you might see quadratic equation, you might see quadratic expression, you might see quadratic function. If it's quadratic function, that just means literally your quadratic is a function. So you'd have to think about what the definition of a function is. If it says equation, that just means you've got an equal sign. If it says expression, it means you've got a quadratic without the equal sign. There are two key forms that we deal with. We have standard form and we have vertex form. So just like earlier, I showed you two forms for the linear equation. We got two different forms that we're going to mess with, if you will, with quadratic equations. So standard form is a x squared plus bx plus c. Notice there's no equal sign there right now as I've written it, so technically that's an expression, not an equation. I just want to clarify. Vertex form, on the other hand, looks a little bit different. I'm going to go ahead and do y equals, just so that you can see like now it's actually an equation. And basically up there, like whenever we dealt with slope and the y-intercept, here you're going to have to do similar things. It's just that we care about the a, the b, and the c, and we'll talk about that in a moment. Vertex form can also show up, and it looks something like this. And so same thing again, the x and the y here are the same x and y you always deal with. It's the same x and y that show up on any graph. It's just that the other parts in here, like the a or the k or the h, like they mean different things. So before I continue any further, I just want to take a moment and kind of let you know that there's going to be like two different pieces to these quadratic equations that you kind of have to wrap your head around. On the one hand, we're going to look a lot at graphs, so you have to understand like the different pieces of it and what it means whenever you actually put it on a graph. The other part is that sometimes you're not going to have the graph, and you've got to be able to deal with these functions as they will usually be, these polynomials that look like this right here in standard form. Which is right here, the standard form, the ax squared plus bx plus c. You'll have polynomials written that way, and you've got to be able to work with them, and sometimes you won't have a graph. So I just want to like point out that you're going to be working on like two different sides. On one side, you'll just be working with the equations. On the other side, you'll just be working with the graphs. But they have similarities, they do overlap, and the graphs tell you things about the equations, the polynomials, and the polynomials tell you things about the graph. Like they're just different representations of the same thing. So for example, let's say you had, let's just go ahead and draw a parabola here. Alright, so first things first, notice I said we're drawing a parabola, and so far I haven't actually put the word parabola anywhere up here in your notes, and that's because parabola is specifically the word for the graph of a quadratic. So for example, if you had something like, I don't know, let's say something like this. Okay, that's a parabola. That is a quadratic. It is a function. It passes the vertical line test. But specifically, we're just worried, like we're interested in certain pieces of this graph. So the first thing I'm going to point out is down here, the bottom of this graph, the lowest point, which I'll mark right there. That's called a vertex. So anytime you hear the word vertex, that's what it's referring to. It wants to know what is this point specifically. Well, notice up here you have vertex form, and that's like that for a reason. And basically what it says is if you're given an equation and it's written in this form, or if you can get it into that form, it will tell you the vertex. So like up here, to continue writing this, usually you'll see where h comma k is your vertex. Now down here, if we go back to the graph, through the vertex is this, I don't want you to think that like it's always there. It's more of like if you're asked to find it, then you can go ahead and draw it. Or sometimes it'll be drawn and it'll just be like this dotted line that goes right through the center. And I know mine's kind of like curving on the screen. It's not supposed to. It's supposed to cut the parabola perfectly in half. That's a limitation with me writing on this right now. But this dotted line, it's usually not there. So in other words, that's why it's dotted. Like it's just letting you know that this is a feature that we're pointing out on this graph. So like I don't want you to look at that and think that it's actually something that's going to show up in your problems like as part of your graph, meaning if you're asked to find like x values or y values, I don't want you to think that this is something that you're necessarily going to be working with every time, because it's not. But if you are asked like to find the middle of the parabola, well, the middle of the parabola is the vertex. But it turns out that if you draw a line straight through the vertex, it actually cuts the parabola perfectly in half. And again, I realize on this particular example, my parabola is not perfectly symmetrical, but you just kind of have to work with me and realize that it's supposed to be symmetrical. So if you draw a line straight through the vertex, and again we usually show it as dotted, there's a word for it, and it's called our axis of symmetry. And all that's saying is basically is that you can think of parabolas as having a middle point that cuts them in half, specifically the vertex. And if you want to draw a line through the vertex, it's going to cut the parabola perfectly in half, and it's just referred to as the axis of symmetry. If you want to describe the axis of symmetry, like if you're asked what is the axis of symmetry, it's really closely related to the vertex, because the vertex is a point. So it's going to have that x and y coordinate because it's on this xy graph. So the axis of symmetry relates directly to those points. Specifically, it's a vertical line, and vertical lines, although you may not remember this, vertical lines are always written as x equals. So like if, for example, I'm going to make something up right here, but I'm going to see something that like is realistic. Realistically, this vertex could be like maybe -4, -3. Like realistically, that could be that point. Okay, so if that was that point and I asked you what's the axis of symmetry, your axis of symmetry is x equals -4. What you're saying is my axis of symmetry can be thought of as the line where x is always -4. Where's the line where x is always -4? It's straight up and down directly through the place where x is -4, which would hypothetically be like right around in there. Okay. There's some other features of this graph that I have to point out, but the rest is stuff you've technically talked about before. So where this parabola crosses the x-axis here and here are your x-intercepts. So where I use the light blue, those are x-intercepts. We care about those. We're going to work a lot with trying to find those. In fact, the majority of what you do in this entire unit will relate back to finding those. And in addition, there's also the Y-intercept. And the Y-intercept is just, again, it's wherever your parabola crosses the y-axis. Notice there's only one y-intercept. If a parabola is looking up, if it's opening up or opening down, there's only going to be one y-intercept just because of the way it's oriented. As far as x-intercepts go, there's two in this case. But like if you took this parabola in purple and if you imagine drawing it somewhere else where like the vertex is just sitting on the x-axis, or the vertex is maybe even up above the x-axis, well, then you've got two scenarios there where you wouldn't have two x-intercepts. If the vertex right here were up above the x-axis, this parabola would never touch it, so you wouldn't have x-intercepts. If this vertex was sitting on the x-axis, well, you'd have one x-intercept, which just so happens would be the same exact thing as that vertex. So the other part that I would like to kind of point out to you right now is that this is considered a positive parabola. It's a positive quadratic because it's opening up, and the way that you can identify that is by looking at the standard form or the vertex form. If A is positive, it's opening up. If A is negative, it'll be opening down. So I'll just kind of show you over here on the side. I'll just kind of draw something so that you remember. So like if the parabola is opening down, that means A is less than 0, meaning it's negative. If the parabola is opening up, that means your A is greater than 0, meaning it's positive. Okay, so those are kind of the key characteristics of a parabola. And it turns out those are just the key characteristics of a quadratic. And there are ways to go about like finding these different things. Obviously, if you have a graph, you can just identify them. But sometimes you'll just have the equation. So notice up here where I said you have h and k, which is the vertex. So if it's written in this form, it just so happens to automatically give you the vertex. Well, in standard form, while we're here, you can actually find the vertex. It's just that it's not obvious, like it's not written in here. And the way that you do that is actually by finding the axis of symmetry. So it turns out that in order to find the axis of symmetry, and I'm going to move what I just wrote, 1 second. All right. So remember, the axis of symmetry runs straight through the vertex. Well, it turns out there's an equation for the axis of symmetry. So the axis of symmetry equals negative b over 2a. So if you can find the axis of symmetry, like whatever you find right there, negative b over 2a, that's also going to give you the x coordinate of the vertex. So here, this gives you the vertex just straight from this form. This does not give you the vertex straight from the form. But notice you have an A, a B, and a C, and you can use those pieces to find the information that you need. Over here, technically, you can get the axis of symmetry from vertex form as well. It would be just x equals h. That would be the AOS, the axis of symmetry. And here, I put the equal sign here. I don't want to confuse anybody, though. Technically, the axis of symmetry is going to be x equals that. But again, since the axis of symmetry has to run through the vertex, if you find it, that x value is the value of the vertex. Okay, so if, for example, you had something like this, you may be asked to like identify certain things about it, and I just want y'all to realize that like if you're asked to identify things about it, you're probably going to have to go back to that standard form and actually interpret it. So in other words, standard form is y equals ax squared plus bx plus c. So if I ask you, for example, to find the axis of symmetry of what's written in black here, this y equals 2x squared plus 5x minus 7, well, the AOS, the axis of symmetry, can be thought of as x equals negative b over 2a. Well, in order to do that, you've got to actually find a and b. So that's why sometimes you might see problems that just ask you to find A, B, and C, and it's just because it wants to see if you can identify it. A lot of students will look at A and recognize that it's part of the first term here, and they will just like write this entire piece and say A is 2x squared. It's not. A is only the coefficient. So I'm going to like connect them right there. Similarly, B is only the coefficient on your second term. And C is only that coefficient, that constant technically, which is -7. So here literally you would say A equals 2, B equals 5, and C equals -7. Okay. So the final thing that I'm going to kind of point out to y'all here is that if you're talking about like domain and range, basically like on this particular example, since the parabola is getting wider and wider, if you're going left to right with your x values, your domain is -infinity to infinity. Your range goes up, your y values, like it's pointing up, so it goes up forever, but your range would start wherever the vertex is. Sometimes the idea of a maximum or a minimum will come up. It'll ask you like, is there a maximum or a minimum? And that's also referring to the vertex. In this case, on this particular example, there's a minimum because that vertex is the lowest point. So, I mean, again, that's really not even like a big stretch. It's just saying like, does this have a lowest point? Yeah, the vertex. So that's the minimum. So if you look over here where I showed you like, if it's positive, it opens up, and if it's negative, it opens down. You can kind of look at those graphs and realize what I'm saying. So like here, the vertex, if it's opening up, your vertex is going to be a minimum. Well, on this one, if it's opening down, your vertex is going to be a maximum. Okay. Final piece of information that I just kind of want to remind everybody of, or to kind of point out. You're going to spend a lot of time factoring. And I just want to clarify that the whole point of factoring is that we want to be able to find these X-intercepts. You're going to spend a ton of time finding the X-intercepts. And the reason for that, honestly, just comes back to a lot of the application problems. So like if I had like, I don't know, a tank or something, and I decided to fire something through the air, it's going to go up, it's going to come down. So if you imagine that as a parabola, then you can kind of visualize like a makeshift x-axis there and like a y-axis here. So to think about this in context, like if this is my parabola, this x-intercept, whatever it is where the tank fired the round from. This x-intercept, wherever it is where the tank's round is hitting. And up here, your vertex would be like the highest point in that projectile's motion. And in fact, that's what you're going to see a lot of. This idea of projectile motion shows up a lot in physics, but it applies directly back to what we're talking about. And honestly, that's where quadratics are going to come in a lot, because anything that has motion that looks like this can be described with a quadratic. And so basically, it's just going to be up to you to find the individual pieces. Again, we're going to go into this idea of factoring, and just to kind of explain what it is. And if you've been watching this whole video, I thank you. Real quick, I'm going to show you factoring. I'm not going to go into great detail. I've actually got other videos that do a good job of showing you how to factor, but I just wanted to kind of give you the initial intuition, which is this. We've already talked about multiplying polynomials. And by the way, quadratics are still just polynomials of degree 2. So multiplying polynomials. We've already done this. And so like specifically, if you remember like x plus 5 times say x minus 7, you could go about that different ways. Like you could just leave it like this and say, okay, well, x times x and x times minus 7 and 5 times x and 5 times minus 7. I get x squared minus 7x plus 5x minus 35 then I do this because I have to combine like terms, and I have my answer. That should look very familiar. If it doesn't, let me know. I'll give you some practice. You can go back and try it again. What we did in our class, though, I encouraged the use of the box method, and I'm going to continue doing that because it forces people to be organized, and it's really not any longer. If you have x plus 5 and x minus 7, you could technically draw a box, because really you're finding an area when you multiply these together. So like x and plus 5 and x and minus 7, since I'm multiplying two things together, two polynomials together, each one of these can be thought of as a term. So if I'm multiplying two terms together, that's like multiplying length and width. So really it's like finding an area. Well, it's the same. That's basically what this is showing you. So x times x, x squared, which we already know, we already did it. X times minus 7, minus 7x. X times 5, 5x. Negative 7 times 5, minus 35. Again, same exact thing that we did here. This is just the other way of doing it. Then you add everything inside the box. Okay. So it turns out that if you have x plus 5 and x minus 7, notice how whenever you multiplied it together, it looks like a polynomial in standard, like the standard form of the quadratics that we were just looking at. And that's because these are technically the same thing. They're just written differently. We call this factored form. Again, I told you there were two forms up there, standard form and vertex form. Technically, this is factored form, and you've worked with it before. Well, you're going to be asked to factor, and what that means is a lot of this unit is going to be all about you working backwards. So in other words, you've all done this part before, and you're now going to be asked to take like something like this, x squared minus 2x minus 35, and you're going to be asked to work backwards and get back to these pieces. The reason why you will be asked to take something like this x squared minus 2x minus 35 and break it back apart into this factored form, x plus 5 and x minus 7, is because if you were to graph this, or if you were to have a problem, and this was the polynomial, and I asked you to find the x-intercepts, this is how you do it. So x plus 5 and x minus 7 tells me that I have an x-intercept. Think about it. Your x-intercept is going to be where your y's are 0. So in other words, what makes x plus 5 0? Negative 5. What makes x minus 7 0? A positive 7. So negative 5 and positive 7, notice they're just like the opposites. Since it's x plus 5, it's going to be at minus 5. Since it's x minus 7, it's going to be at plus 7. These are your x-intercepts for this parabola. Like, just that fast. It's positive, it opens up, so that means if I were to graph this parabola, it's going to do something like this. I know that looks horrid. And that's how you do it. And last but not least, that minus 35 is your Y-intercept. So, if you're asked to graph one of these, it's helpful to be able to factor it. If you're asked to find the x-intercepts, though, you have to be able to factor it to find the x-intercepts. And so just to clarify, what I'm saying is like you'll have something like x squared, I don't know, plus 5x plus 6, and you'll be asked to factor that. And if you're asked to factor that, basically what it's saying is something got multiplied to give me this. Something was multiplied to give me x squared plus 5x plus 6. Well, what was it? And you're going to be expected to figure out how to fill in the parentheses basically with like whatever you started off with. So up here you had x plus 5 and x minus 7. Well, down here, what does it take to get to that? I can quickly tell you it's x plus 3 and x plus 2. But the challenge is going to be, how do you get from x squared plus 5x plus 6 to x plus 3 times x plus 2? Like, how do you go from here to here? That's what factoring is all about. And that's what you're going to be spending a lot of time on. So that kind of concludes my introduction to these quadratics. Hopefully this will give you enough information between this and the other videos. You should be able to get going. And I'm going to have some problem sets and stuff like that coming for y'all. And if not problem sets, then just additional stuff in Delta Math. If you have any questions, of course, let me know. Take care, everybody.